Hello, this is Chuck Ridgway, Automation Technology Manager here at Horner. Now, we fully intended to bring you this topic today live, but unfortunately we ran into some of those technical gremlins, so we had to pre-record it. That being said, we have a great topic for you. Today it's all about using the I/O simulator with the Micro OCS. Now, the I/O simulator is a great new product that I've talked about before, and I would have talked about it more, except we keep selling it out every time we make some. Now, we've got another production run in the works, so you've actually got a chance to get your hands on one, so I thought I would go ahead and talk about it again. Okay, now why are we talking about the Micro OCS while we're talking about the I/O simulator? Well, that's easy. Those are two products that really work well together. If you're a new engineer or a beginning automation engineer and you're just learning, the Micro OCS and the I/O simulator are a great way to do automation labs and to experiment and for you to learn your craft. If you're an experienced automations engineer, you know that the Micro OCS is entry level in name only, and there are so many applications you can do with that controller. And as an experienced engineer, you also know that anytime you can test your code in advance using something like the I/O simulator, you're going to be miles ahead once you get to the field. Okay, now this is the point at which I usually bring in my colleague Casey Gardner to talk about the topic a little bit, but because of those technical gremlins, we're not able to do that. Now, if you're watching this live, go ahead and chat in your questions. We'll get them answered just as soon as we can. If you're watching this on replay, we still want your questions. Just go ahead and type those into the comment section, and again, we'll get them answered just as fast as possible. Okay, let's get started. Here's how I've broken down the topic for today. First, we're going to spend a few minutes talking about the Micro OCS and the I/O simulator individually. Then we're going to do a quick unboxing of the simulator. We've made some changes over the past few months, and we wanted to show those to you. We're going to talk about what you'll need from a tool standpoint. Now, you can use the I/O simulator with just about any controller out there, PLC, all-in-one controller, you name it. And of course, it works fantastic with the Horner OCS. So there's a lot of ways you could hook it up. We're going to talk specifically about wiring diagrams for connecting it to the Micro OCS Model R relay output version, as well as the Model A DC output version. Then we'll talk and show you how to wire it up and test it out. Let's start with the Micro OCS. What is the Micro OCS? This is our entry-level all-in-one controller, but as I mentioned in the open, it's entry-level in name only. It's really the best all-in-one controller for simple applications. It's currently available in 4 different models: an X2, which has got a simple key-based user interface and has a very low entry-level price. And then everything up from there has a color screen as well as Ethernet support, and the screens range from 4-inch to 10-inch in size. Now, regardless of what size of unit you choose, you have 2 different options from an I/O standpoint. You've got the Model A, which has 30 I/O points, 12 digital in, including high-speed counting, 12 DC out, including high-speed outputs, 4 to 20 milliamp analog in, and 2 4 to 20 milliamp analog out. The 4, 7, and 10 also support, with a limited range, RTD PT100 temperature sensors. The Model R is identical to the Model A. The only difference is, instead of 12 DC outputs, it has 6 relay outputs plus 2 solid-state high-speed outputs. Okay, that's the Micro OCS. What is the I/O simulator? Well, this is really a versatile tool for testing your application logic by simulating I/O signals on your desk or in the lab. The I/O simulator has 8 slide switch inputs, 8 LED outputs. It has 2 pots that can be used to simulate 4 to 20 milliamp sensors. It has a pot that simulates an encoder. It has another pot that simulates an RTD temperature sensor, and it has a couple of test clip points for measuring the 4 to 20 milliamp output from the OCS. Again, it's compatible with way more than just Horner OCS, but it's a great marriage between the two. It's compatible with all our Horner controllers and most third-party controllers as well. You can use it on DIN rail, you can use it in the lab, you can use it on your desk. All right, now included in the kit are a power supply, and it's a 24 volt, 1.5 amp power supply. And that power supply is ample for providing power for the OCS as well as for the simulator itself. You also get 2 cables. One of them is marked output, but otherwise they're identical. And the cables have color-coded wires, and all the wires are terminated with ferrules to make connections really easy. Next, let's go to unboxing, and let's see what you'll need from a tools standpoint. Okay, let's take a look at the I/O simulator and what comes in the box. So we've got the HE-TK001 I/O simulator. Let me go ahead and open this guy up. All right, so inside we've got the simulator itself. Let's take a look at this first. Okay, it comes inside some packaging to protect against static, ESD. All right, so this is the simulator itself. Okay, here's the input connector, the output connector, labeled J2, J3. Here's the barrel connector where we add power. We have a fuse with this version, so the latest revision has a fuse as well as a power LED. Everything else looks pretty similar to previous revisions. We've got 8 switches, slide switch styles. We've got an encoder or pulse generator. We've got a couple of pots that simulate a 4 to 20 milliamp signal. We've got another pot here for RTD, and then we've got a couple of test clips or test points where we can test our 4 to 20 milliamp output from the OCS. Okay, so there's the simulator itself. Let's see what else is in the box. Okay. Got a power supply here. This is the power supply that's going to power everything up. There's enough power here to power both your OCS as well as your I/O simulator. In almost all cases, I believe it's a 1 amp supply. And then digging a little deeper here, you'll see we have 2 cables. All right. They're labeled out, or at least one of them's labeled out, so that you can assume the other one is in. And these cables come pre-terminated with ferrules, which is nice. Okay, another thing you get in the box is you get a spare fuse. So if you blow the fuse right out of the gate for whatever reason, the first time you power it up, or the first time that you wire it up, I should say, you got a spare fuse to take care of you there. Okay, so that's a quick view at what comes in the box with the I/O simulator. Now, comparing it against previous revisions, this is the original version. The main differences are really a lack of a fuse on this original version, no power on LED either. And then I know with the first version, the action of the switches was down equals on, which could confuse some folks. And on the milliamp 4 to 20 milliamp pots, the action was down for the signal to go up, and that confused some folks as well. So we took care of that with subsequent revisions, including the latest one, which I just showed you, which, as you can tell, is green in color. Okay, let's take a look at all the things we might need if we're going to connect up this I/O simulator. Of course, you're going to start with the simulator itself, along with the cables and the power supply that both came in the box with the simulator. Of course, you're going to need the I/O terminals and the power terminal that were included with the Micro OCS or whatever OCS you're going to wire it up with. And, you know, other than this flat-bladed screwdriver, a fairly small one, not tiny, but fairly small, that could be all you need. However, if you're going to be using, let's say, the relay version, and you need to build up a jumper assembly to jumper the V+ signal to all the relay commons, then I'd suggest you also get maybe a couple feet, this is only about a foot, but maybe a couple feet of small gauge wire. I think this happens to be 20 or 22. That's perfectly fine. And in that scenario, again, if you're building that jumper assembly, then you'll need some cutters, you'll need some wire strippers, And then I would recommend, to make things nice and neat, I would recommend ferrules and a ferrule tool to kind of round out the tools that you would use to come up with a nice system. And if you're, a engineering student and you're just kind of getting started in automation, I would highly recommend that you pick up some of these tools if you don't have them already. They just make it easy for hooking things up in the lab for whatever it is that you might need to simulate as part of your job as an automation engineer, or even as a student for some of the projects you work on as a student. Again, so these are some of the things you might need as you're hooking up the I/O simulator. Okay, let's talk wiring diagrams. Let's figure out how we want to connect our Micro OCS to the I/O simulator. Now, this is where I tell you that there certainly are wrong ways to connect the two. That's why we have a fuse included. However, there are multiple right ways to connect the Micro OCS and the I/O simulator. So just because you may want to do some variations to what I'm showing you here, that doesn't mean that what you're doing is necessarily wrong. Not all applications are the same. Not all applications have high-speed counting, RTD temperature sensors, high-speed outputs, etc. You get my drift. So you may choose to connect things slightly differently, but again, that doesn't make it wrong. All right, now let me show you my example of a pinout for a Micro OCS X4R. That's the X4 with a 4.3-inch screen with the Model R I/O option that it features 6 relay outputs and 2 solid-state high-speed outputs. Okay, we're going to start with the input cable, which connects to J2 on the simulator. All right, I've got the pinout that I've chosen shown in that table there. I'm taking advantage of all 8 slide switches that simulate inputs. I'm taking advantage of the encoder knob. I'm also taking advantage of both 4 to 20 milliamp potentiometers that simulate 4 to 20 milliamp sensors. So there's my pinout. Now you'll notice that most of the conductors will connect to J2 there on the right, that middle connector where most of the inputs are connected. But there's also a few conductors, 3 to be exact, which I'm recommending that you connect to J3, which is the analog connector. One other thing that's important to know about the Micro OCS, all the pins on all 3 Micro OCS I/O plugs, all those plugs have common terminals, and they're all with the same potential. And that potential is also the same as the minus lead on the 3-pin power plug for the Micro OCS. So on my diagram, when I show C, it doesn't really matter which C terminal you pick. I've just picked one. All right, now let's talk outputs. And outputs are primarily connected on the OCS side to the black J1 connector. And then the other end of that output cable is going to connect to J2 on the I/O simulator. You can see my pinout there. It takes advantage of all 8 LEDs that simulate output signals. It also takes advantage of the set of test leads for testing your 4 to 20 milliamp output from the OCS with a multimeter. It also takes advantage of the built-in potentiometer for simulating an RTD PT100 temperature sensor. A couple things I will note here. First of all, there is only 2 wires that are connected to V+, which is 24 volts. One of those is allocated to go to your 24 volt power plug on the OCS. The other one will need to be used to power not only V+ on the high-speed outputs, but it will also need to be run to the common terminal of all 6 relay outputs. And I've shown all those connections circled in red. So that means you're going to have a little work to do from a wiring standpoint to make sure that you come up with a jumper assembly for making those connections, but we'll show you how to do that. Now, what if you have an X4A or any Model A Micro OCS, for instance? The Model A, remember, has 12 DC outputs instead of 6 relay outputs plus 2 solid-state high-speed outputs. With the X4A, it's pretty straightforward. The only changes really are in the part of the pinout that I've highlighted in red there. While you don't have as much jumpering to do with the X4A as you do with the X4R, there's still a little bit of jumpering to do. Again, one of your V+ wires is allocated for the power plug. The other one needs to be jumpered between the two V+s from the two groups of DC outputs. Now let's take a look at how you wire it up. Okay, let's get started on our wiring procedure. We are going to begin with the input side of things from an OCS standpoint. So I'm holding the OCS input connector in my hand. Now, I can't stress enough how important it is to have a plan. So make out a list of what wire colors are going to go on which OCS I/O pin. I've done this very thing and printed out the results. And when you have a plan, it makes it really straightforward and really accurate to get everything landed where it needs to go. Okay, so my plan calls for the black wire to go on I1 and the brown wire to go on I2, and then it continues on from there. We'll go ahead and get these first two wires landed live here, and then we'll go ahead and do the rest of them offline. Okay, so the ferrules are really nice. They make it easy to get the wires in the right location smoothly. They also prevent any loose strands of copper from getting where they don't belong. So I've got the first two wires landed, and I'll finish the rest of them offline. Okay, now we're going to move on to the output connector. We finished up our input connector. We've got all those connections made where we want on that orange connector. Now we've moved on to our output connector. So let's take a look here. Of course, we've got our output terminal block. We've got, again, clear plan on which color is going to which pin. Now with the outputs, there's some slight variations here to be aware of. So, you know, we certainly have pins like R1, R2, R3. Those are the outputs from the individual relays. Those are going to have single wires plugged into them from our cable. However, the common wires for the relays, C1, C2, C3, all the way through C6, along with the V+ terminal here for the high-speed outputs, those all need to be connected to 24 volts. That means we're going to need a jumper assembly connecting those particular pins, and I'll show you that in a little bit. But we'll just get started on the output side by connecting up our outputs as well as our relay signals, and then we'll come back to the jumper. So let me just put a couple of these in here for you. I need to have the black wire connected to Q1, so I'm going to go ahead and do that here. All right. Again, this is very much like we did with the orange connector. Okay, for the inputs. There we go. We got our black wire in Q1. Next, I need my brown wire on Q2. I'll go ahead and get that taken care of. All right, and then after I finish this one up, we'll go ahead and start on the relays. And then my next plan is for my red wire, which is buried down here somewhere. Let's get him out. Okay, my red wire now, I want him up here on R1 because he's going to be driving, that relay will also be driving LEDs. R1 will be driving the third LED in my simulator. Okay, and then I'll just go through my plan for R2, R3, R4, R5, R6, etc. And then we'll come back and work on the jumper assembly. All right, next we're going to talk about that jumper assembly that's going to run the 24 volts or V+ signal from all the relay commons to the next, and also to the V+ terminal for the high-speed output. So in preparation to make this little jumper assembly, I just cut 7 little segments of wire here. This is, I think, 20 or 22 gauge wire. I stripped off both ends here. You'll notice all these wires are a couple inches long, maybe 1.5 inches, 1.75 inches. And I've got one that's a little bit longer, just because that one has to stretch from the last relay common over to the high-speed output common. So really what I'm going to do here is I'm just going to take these, see if I can show you here. And because these wires are pretty small, I'm going to go ahead and just twist these together. Okay, you can see there. Then I'm going to take one of these ferrules. If I can grab this. Okay, I'm going to slide the wire in here. Now, of course, you can use double ferrules for this, which would certainly be an option. But you see, I've got that ferrule in there, or those two wires inside the ferrule. I'm going to go ahead and crimp that down. So now what I've done is I've created, or I've joined these two wires with a ferrule. Next, I need to do the same thing with the next wire segment. Okay, so I'm going to flip this around here. I think you'll probably get the hang of it once I get this one done. And you can see, again, I'm going to twist the next segment on here. All right, add the next ferrule. Make sure I get that in there well. Crimp that guy. Okay, and you can see that I'm kind of working my way down the line, and I'll go ahead and add another segment. I'll do that off camera, and when I'm done, I'll show you what I've got. Okay, I finished up my jumper assembly here. I had miscalculated. I had one wire too many, no big deal, just didn't end up using it. And my output cable, there's my output cable that pretty much has everything connected to it except for this jumper. And what we're going to do here is this gray wire is where the V plus signal, the 24 volts, is coming in from the simulator. We're going to cut this ferrule off, put a new ferrule on with these two wires, okay, and that'll be our connection, the first V plus connection that'll go into the common for relay 1, and then we'll be going into the common for relay 2, 3, 4, 5, and 6, and ultimately finishing up with just the single wire in the V plus terminal for the high-speed output. So that's what we're going to do. Okay, so all we need to do here is we'll take our cutters, we'll cut off this ferrule, because obviously we don't need this connection now. What we'll do is we would normally use our strippers. I'll cheat here and use my cutters. Just be careful. There we go. I'll get these wires bundled there, combine with our jumper assembly. Okay, add a ferrule here. All right, and then we'll make that connection. And now, let me see if I can show this to you. Okay, so now we've got our jumper assembly made, and we're ready to connect it to our output terminal strip. Okay, so here's what things look like when we're all done with our cable assemblies. Okay, here's my input connector with all the connections landed. Okay, a few of the pins or the conductors from the input cable also land on the analog connector. I didn't show that to you specifically, but that's what you end up with here, with a few of the conductors from the input cable going to the analog connector, and then a few of the conductors from the output cable also going to the analog connector. Okay, here's our output connector, as you can see, with the jumper assembly already installed there, connecting the V plus 24 volt signal everywhere it needs to go. And then in addition to a few pins on the output connector going to the analog side of things, a few, or two exactly, conductors are going to your power cable to power your OCS. And one thing I forgot to mention while I was doing the unboxing of the I/O simulator. Now, in my case, of course, I'll be able just to snap it on DIN rail because I have DIN rail on my desk, but you may not have DIN rail on your desk. But don't worry, we've included some adhesive dots on the back here. These are those kind of booger glue dots that stick really well, but they also come off really well and don't mar any surface. So these are also really nice for keeping the simulator on a flat surface in place despite the fact that, the cables may be tugging on them a bit, and it'll keep the simulator where it needs to be. All right, so that's what things look like when we're all done with our wiring. Okay, now that our wiring is all done, let's try everything out. Let's take a look at our test bench here. Of course, I've got a DIN rail, which I've got the I/O simulator mounted to. If you don't have a DIN rail, remember, you can use those adhesive pads on the bottom of the unit. Let's just start with taking a look at the cabling. There's my input cable. Here's my output cable. The other end of these cables is connected to the I/O connectors that's plugged on the underside of the Micro OCS. My barrel connector is here. That's where my 24-volt wall-mounted power supply is connected. You can see I've got a fuse here in case things go horribly wrong. Let's start by taking a look at the inputs, specifically the slide switches. So we have 8 slide switches total. I have 4 of them shown on the screen. So as I turn the switches on, you can see my indicators on the screen light up as well, and then I'll turn them off again. Okay, there are 8 LEDs for simulating 8 outputs. Now on the first output LED, I've got that connected to a high-speed output, and you can see it's flashing at a somewhat maybe 10 times a second type rate. All right, so here on the screen, I can set the duty cycle and the frequency for that high-speed output there. Now I've got the duty cycle set at 50%. 16,000 over 32,000 is 50%, and I have the frequency set at 10 Hertz. Let me go ahead and adjust that down to 5. You should see that LED slow down. I'll adjust that down to 2. You can see it slow down even more. Okay, so that's one of the high-speed outputs that I have connected to the first output LED. On the second output LED, I have another high-speed output connected. I don't have anything on the screen there to demonstrate that with, however. However, with the third and fourth LED, those are wired to relays. Okay, so I can flip a button here to turn that relay on, which in turn turns on LED number 3. And I can do the same with LED number 4. And I've got 4 additional LEDs that I'm not demonstrating right now, but they are connected. Okay, next let's take a look at the analog side of things. Oh no, before we do that, let's take a look at our encoder. This is a encoder wheel. So you can notice as I turn it clockwise, it counts up. As I turn it counterclockwise, it counts down. Okay, that can be very handy for simulating a variety of applications. Now let's take a look at analog. I have 2 pots that simulate 4 to 20 milliamp sensors. Here's the first one. Over here on the right, that's that yellow bar and also the top data field there. So I'm raising up the 4 to 20 milliamps and now I'm lowering it back down again. The second pot is connected to this blue bar graph as well as the second data field from the top, and I can exercise that up and down. And then next we've got our third pot, which has to be operated with a screwdriver. I've just got a small flat screwdriver here. And this one, as I move it clockwise, you'll notice the temperature going down. That's shown in the third data field from the top there. And as I go counterclockwise, you'll see the temperature going up. Now, the Micro series supports RTD PT100s from minus 50C to plus 200C. And that RTD pot, or that simulating pot, approximates that range beyond it, above and below a little bit. Okay, and finally, let's take a look at our multimeter here that's connected to these handy dandy test clips for the clip leads. So right now I've got a data field here that's driving mid-range on a 4 to 20 milliamp output. So 16,000 counts is putting out right about 12 milliamps. If I go to minimum, which is 0 counts, I'll go immediately down to 4 milliamps. If I go to maximum, which is 32,000 counts, you'll see I pretty quickly go up to just about 20 milliamps. Okay, so I've taken advantage of most of the features of the I/O simulator, connecting those up to the Micro OCS, and I think we've got a really nice benchtop system here that I can use to test out any code that I write before I get to the field. Okay, before I wrap things up here, I thought it would be important to show you the Cscape configuration and a little bit of programming and screen work that I've done on this demo here. All right, let's start with the hardware configuration. All right, I'm going to go to the local I/O tab, press config, module setup, and let's start with the digital input. So on the digital input side, I've set it up for positive logic, which is the default, and I've set the first high-speed counter to quadrature. So that means the first two physical inputs are going to be used for quadrature counting. Remember, those are connected to my encoder wheel, and the first input leads and the second input lags, and when that happens, I count up from a quadrature standpoint. Okay, so that's my configuration of my digital inputs. On the digital output side, I have configured my first output as PWM. Okay, that's where I showed you that blinking LED by changing the duty cycle and the frequency. I guess I remembered wrong. I thought I had set up the second output for high speed as well and just didn't put anything on the screen. Turns out I set that one up as just kind of a normal output. Okay, so those are the digital output configuration. Let's take a look at the analog input side. I have 3 of the analog inputs configured. The first 2 for 4 to 20 milliamps, those are tied to the 4 to 20 milliamp pots, and the third one is tied to that pot that's simulating a PT100 RTD. I've added a little bit of filtering there to make sure the readings are relatively stable. Okay, and then on the analog output side, I've basically disabled the first analog output because of the fact that RTD number 3 and analog output number 1 share the same pin on the terminal strip. So if I use the third analog input as an RTD, I can't use the first analog output. But that's okay. In my test system, I only had 1 analog output, and I set that up as AQ2. And I set that up as 4 to 20 milliamps. Okay, so that's the hardware configuration. All right, next let's take a look at the variables I created. Now there's literally a million ways you could create variables. In my case, I didn't use arrays for my variables, although you could for sure. Most of my variables were added in the global group, okay, because they were mapped to real-world I/O points. Now I used variable-based ladder here, so I only have to do memory mapping when I have I/O related type variables, or maybe when I'm using like Modbus or another serial protocol or Ethernet protocol. But in this case, of course, I'm talking about I/O simulation, so a vast majority of my variables are mapped to specific memory locations: I's, Q's, AI's, and AQ's. Here's my high-speed counter accumulator variable. I've got a variable that's an integer assigned to read in the RTD. Okay, that variable, there's a little bit of logic here for converting that raw integer over to a floating point degrees C reading. And those variables are listed down here under retained variables because they're not directly mapped into I's, Q's, AI's, and AQ's. For my analog inputs, I have a couple of integer-based variables to read in directly those 4 to 20 milliamp analog inputs from number 1 and number 2. I've got my settings for my high-speed output, duty cycle, and frequency. And then I just did some simple variables for the first 4 switches, which are tied to the first 4 inputs. And then for 3 of the 8 LEDs, I've set up simple variables for those as well. And then I have my milliamp output variable that's an integer. That's the one I manipulated from 0 to 32,000, and you would see the result by the readings on my multimeter as that current reading changed. Okay, so that's what my variables look like. Let's just take a really quick look at my screen. Okay, I just did a single screen. These are pilot lights that are tied to the slide switches. So there's my SW1 variable for the first slide switch that comes in through I1. My switches or toggle switches here are tied directly to the variables that are driving relay 3 and relay 4. Here's the accumulator on my high-speed counter. Here is the settings for duty cycle and frequency for my high-speed output. And here are all the readings for my analog channels, the 3 inputs. The first 2 are 4 to 20 milliamp, the third's RTD. The fourth is the milliamp output, which is tied to AQ2 in this particular case. And then I've got my bar graphs for also indicating my first 2 4 to 20 milliamp analog inputs. Okay, so that's a quick run through the Cscape configuration for the demo system. Okay, that wraps things up for today. Don't forget to subscribe if you haven't done so already. And remember, we're here every Tuesday at 2 o'clock, as long as we don't have any of those nasty technical gremlins that got us this week. And next week, we cover a really fun topic. We're going to give you some helpful Horner hacks, some little tips and tricks that you won't find in the user's manual, ones that I'm sure you'll enjoy, and ones that I'm sure you'll be able to take advantage of at some point in your career. All right. Once again, I'm Chuck Ridgway. Thank you for joining us, and we'll see you again next week.